Okay, this video will be about support vector machines and how can we use quantum machine learning to enhance these models, right? So firstly, like, what is the job of a support vector machine? It's just basic classification. You have two classes. One is the +1 class, so where the true label should be +1, and one is the -1 class where the true label should be -1. So these are our yi values. So yi for all I is in 1 and -1. Of course, you have some xi as the input features for our data. So as usual for any machine learning process, we have the data x comma y, where these are like vectors. This is more of a matrix really, right? And so for each data point, we have the features xi and the target yi, right? So our prediction will be basically yi hat is just equal to the signum of this linear function, which is just omega transpose or w transpose or whatever, plus b over here. So it's just a dot product between some vector and then x plus b. Now what we want to do is just maximize this margin, so that's 1 upon the magnitude of omega, right? But then maximizing that, it's pretty much the same thing as minimizing this quantity, or in fact even minimizing this quantity. So it's a norm of this omega thing squared upon 2. So I'm adding this upon 2 because it's convenient. That's pretty much the only real reason I should be adding it. But yeah, you could view it in some other way as well. Okay, so that's there. But then we have to do it, so we have to minimize this thing under some constraints. So we minimize this, of course, with respect to, so the only thing that we can really change is just this omega thing and the b thing. So minimize with respect to omega and b. I'm really saying it's omega, it could be w or any other variable, it doesn't matter. So minimize with respect to omega and b, but under some constraints. So our constraints are that each of these points should be correctly classified. So what should happen is that w transpose x plus b, that should be bigger than or equal to 1 if your true label, so it's xi over here. So if your true label is equal to 1, and at the same time, if it's -1, then this should happen. So we can combine both of these conditions into a single condition, that is yi times w transpose or omega transpose xi plus b, that should be bigger than or equal to 1, right? So what we can do is that we can penalize we can penalize the model every time it does not have it, and we can penalize very harshly. So what we'll do is we'll have this loss function, which is just a function of omega b, and we have this new thing which is alpha. So alpha is also a vector, or you can just think of it as a bunch of values. So our loss function will be of this form. So you of course have this thing, this so I'm just going to write it as omega square by 2, but it's supposed to be the norm of omega square. I mean, I'm assuming you already know what I'm talking about. Okay, plus, so for every single of these points, we'll penalize by something. So we'll penalize by alpha I, which is sort of like a Lagrange multiplier. So it's a positive quantity or equal to 0, that times of, so this, if it's less than 1, then what we kind of want, we want to penalize. If it's bigger than 1, it's actually a good thing, right? Then yeah, whatever, it doesn't really matter. So we just have 1 minus this quantity, so just yi times this whole thing, right? And this is supposed to be summed over all the samples, right? So that's our loss function. So here's the fun part. Instead of just minimizing this overall, which is what we usually do when we have equality constraints, right? So if we just had equality constraints, we would just minimize it completely, like over omega b and alpha. But over here, that's not quite this. It's not quite the thing. What we want to do is enforce inequality conditions, and the way we'll do that is by setting something like a min-max problem. So what we'll do is we'll minimize our loss function. So our loss function is some omega alpha and b thing, right? So we'll minimize this in omega and b, sure, but we'll actually maximize this in alpha. So remember, all of these are just vectors. So what this will have the effect of doing is that whenever you have a penalty, right, since we want to maximize with alpha first, it will just make it go to infinity straight away. It will just make it go to infinity, and then that's not the minimum. Like you cannot have a minimum at all, because yeah. And so what will happen is, for whatever omega and b you are trying to calculate the loss function, we'll just penalize it to the extreme, to like infinite, if one of the conditions isn't met, it's violated. And at the same time, if yi times w transpose xi plus b, if this thing is bigger than 1, right, that the condition is met and it's met more than what is really required, in that case our alpha I will go to 0, because then this whole quantity will be negative. So the only sensible thing to do is let alpha I go to 0, and so we do not penalize those kind of points. And so this trick sort of helps us like achieve all of these things, right, at the same time. So our whole whole problem boils down to just this little thing. So it's just a min max problem, or you can equivalently state it as a max min problem. So maximize for these multipliers alpha, minimize for some omega and b, right, over omega and b is what I should say, this thing. Now this is a problem which is quite solvable really. This one not so much, but this is in fact very solvable, right? So for whatever alpha values you have, you can solve this inner problem very easily. Since our loss function is just this thing, it's omega square by 2 plus summation of alpha I times this thing 1 minus yi w transpose x plus b, right? So we can just take a gradient of this with respect to omega and with respect to b, and then just equate it to 0, right? So Laplace sub omega of L, that's just going to be, so this 2 comes out and cancels with this half, and that's why we had this half in the first place. So it's going to be like omega plus, so you can think of it as omega transpose omega, but just I like to think of it as just vectors at this point, like it's a dot product over here. Anyway, so it's just plus summation over I of alpha I, and then taking this inside, it's just this one doesn't really matter, so it's just negative yi. So this is just a dot product, so this we really can just write as xi directly, yes, and then so minus yi b, right? So since b is not like it's independent of our omega stuff, so this is all we really have. So we want to set this to be equal to 0. So what happens is our omega is just equal to summation of this quantity alpha I yi xi. So remember, this is a vector and this is a vector. Similarly, we can take a derivative with respect to b, and since b is a single quantity, I'm just taking a derivative, like, so it's going to be like dl by db, or more like partial l by partial b. So that's going to be what? That's this term is like independent of b, so that doesn't matter. This one doesn't matter. You just have this thing, negative summation of alpha I yi. So omega transpose x doesn't matter. This b thing just becomes 1. So this is the whole thing, and this should be equal to 0. So what that means is summation of alpha yi is equal to 0. Alright, so now that we have these things, these equations, we can plug that back into a loss function, which is just this thing, and get a new formula for the loss function. And so now we have solved this inner problem, and so it just becomes like maximization or alpha. But what's the loss function? Our loss function is just half of omega square, just like half of this quantity squared, right? Yeah, well, I don't know how to exactly say this, but whatever. So it's just, yeah, so it's just like summation of I phi yi xi vector squared, sure, plus, so summation over I. I'm going to break this up into a bunch of parts. So first is just summation over I, and then alpha I, just like that, right? Because there's a 1 involved over there, right? Yeah, I was going to say something. Oh yeah, okay, so this is just part. Then minus summation alpha I yi, and then omega transpose xi, right? But then you can make this omega transpose come outside, right? It's linear in the end, right? And so this summation is the thing. But then remember, omega transpose is just this thing transpose, so it's just once again the same thing as before. It's like a dot product, so this just squares this whole thing directly, right? And then finally you have this term, so it's minus summation of alpha I yi b, so b comes outside, but remember that this quantity is 0, and so this term is gone, and so all you have is just this. It's so firstly this and these two are these are like terms, so it cancels. So you just have this loss function. You have summation of alpha I because of this thing, minus, so it's square pretty much, so it's just summation I, it's alpha I yi, and then you have x I over there squared, right? Amazing. So let's just see if we did this correctly. Yeah, it seems like the thing. Right, and we want to pretty much just maximize L. So maximize L under some constraints. So under the constraint that your summation of alpha yi should be equal to 0, right? But then this thing you can actually break very smartly into something which will, so this is a vector by the way, right? So essentially if you had to calculate this, what you would actually do is just compute these quantities, right? And then do a element wise sum, and then yeah, so those kind of things. There's a bit of a stuff involved in there, right? But then you can also break this into something better. So you can break this as negative summation of, so summation over I j alpha I alpha j yj, and then it's more like a dot product. So it's just xi vector dot xj, and I haven't like done anything complicated. All I have done is just broken it as a dot product, so it's a vector in the end. So you can just write it as this thing, summation of I alpha yi xi vector dotted with summation of alpha yi xi vector, right? Yeah, and then this just boils down to this summation. And so over here the nice thing is all you really have to do is just compute these quantities, these dot products, right? Once you can do that, yeah, so like if you just have some way of evaluating these things, after that point it's very simple. Like you just have to compute this quantity, right? Which isn't too complicated, right? Yeah, agreed. So this is usually useful when you have like less number of data points. In that case, let's say you have like n data points, this would be something like order n square. Cool. And let's say you have quite a bit of dimensions, right? In that case it would make sense to do it like this, right? If you already knew the dot products, you don't have to do all of this stuff. You don't have to sum it up and then do stuff like that. This is going to be like order n times of, so whatever number of things you have times k, and this is going to be just order n square. So if your n is like small and k is big, then this makes perfect sense to do, right? So why are we concerned with this kind of a scenario where like k is large and n is small? The problem is that most data is not linearly separable. So in that scenario what you have to do is you have to add extra terms, right? So usually you just have like, you just extend your basis or your features. You create new features by using something like a Gaussian basis, or like some Fourier basis, or the most popular one is just using a polynomial basis, right? Like some basis function is what I'm talking about. Okay, so you can do the same thing over here as well. Just, you know, calculate extra features, and then if you know the dot products with those extra features, then that's very nice, because it like really cuts down on the computation. So this is where the kernel trick comes in. So what we want to do is we want to be able to evaluate this dot product. So it's xi vector dot xj vector, which is sometimes also written in this fancy notation as something like xi vector comma xj, something like that. Anyway, so we want to be able to like evaluate this inner product. Yes, I'm going a bit too fancy, but trust me, it's worth it, as this thing. So it's something like this. Actually, I shouldn't really say this. So it's not this that we evaluate. Instead, what we do is, instead of this, we evaluate this thing. So our xi vector, we transform it to give us a bigger vector as, let's say, let's call it like phi of xi. Similarly, this we can you know, expand, right, by adding more features, and so it's phi of xj. And the dot product between them is now what we would go for, because now where this capital X thing has been changed to some x dash with more features added in, right? So this x dash is just this stuff is just equal to like phi of capital X, something like that. Sure. So then these inner products is like what we really want to use, right? So this is called the kernel trick. It's useful and whatever. Yeah, but this is still not enough. Sometimes you really need like a lot of vectors. So even if you can actually compute this quantity easily, right, if you can compute it without actually referring to this phi function and just using something like, I don't know, just some k of xi and xj, right? Even if you can do that, that's still not enough sometimes, right? Because like you might not actually be able to figure out what sort of like phi do you really want, because it's not like that all phi actually have this nice property that you can write them as just some function k of xi vector and xj vector, right? It's not, I mean, of course it's like a function, but what we kind of want to do is write it as some sort of how do I even say this? I don't know how to say this. Yeah, this is, I really don't know how to say this exactly. Okay, I should say it like this. It's like the kernel is applied. It's supposed to be a bilinear function, pretty much, right? It's supposed to be just based on the dot products. So essentially, or most favorably, what you would want to do is just use the dot products themselves. So it's just this thing, right? So just calculate these dot products, and based on that you can completely figure out this stuff. That's kind of our goal. But yes, of course, most of the times this isn't really possible. So instead, what we kind of want to do is so why I'm saying it's not possible is that it's hard to be able to like reach all of the space. So like, let's say you are now going to an n-dimensional space, so it's very hard to be able to reach all of that n-dimensional space just by using something like this. Like just by using a phi that actually has this property, we are very much restricted. So instead of that, what we kind of want to do is use quantum computing to calculate these things, these inner products, directly without actually ever referring to the kernel at all, right? So your phi will be like a real function. This thing won't just be computed like, you know, using the kernel trick. Instead, you are going to actually compute your phi of xi, but it's going to be much cheaper and much more it's much faster than if you were going to do this normally, right? So yeah, let's just get to it. So the whole idea is that you're given n features. So you have xi as some n features, right? You normalize this thing, so you get some xi tilde where all the features are in like 0 1. So this is just 0 1 to some power, I don't know, or you could just say 0 to 2 pi. That also works. It's not a big deal. You could have any sort of range really, but let's just go with 0 to 2 pi to some. So it's to the power of n, right? Each feature is going to be like this, and then what you do is with this you create a gate, that is a quantum gate, which will be like let's call it like epsilon xi tilde. What this does is it takes in some ket 0, right? So you have some ket 0 vector, so you have like some m qubits, right? So you actually have like m qubits, all of them with the 0 vector as their initial state. So this is like a register of m qubits with the 0 ket state. Then you put all of that through a quantum gate, right? When I say put through it, we really just mean like apply the quantum gate on our register. There's no actual circuit as such. It's just a bunch of operations that our machine does. So if you're not sure like what I'm talking about, you are still thinking that there's some hardware which we are building, you could like go to this quantum abstract machine page on Wikipedia and just take a look, and you'll realize that it's not some hardware which we are building. It's like we are using the hardware to do some instructions, mainly quantum gates, on our register, quantum register, right? So the state vector was initially just 0 ket, that is for the full all qubits combined, right? It's like m qubits. Now you have this gate epsilon psi tilde, right? And this gives you something. So most of the times this will just give you like so like you have something like a ZZ feature map by Qiskit or something like that. So some standard thing will happen. So xi tilde, the features in this vector, right? So the entries, they are pretty much like parameters for single qubit gates and also double qubit gates. So like you have some control gates which we apply on this on these m qubits, and that gives you some vector. So it's just some epsilon xi tilde 0 ket, and this 0 ket is it's a different thing than this 0 ket. This is for like a single qubit, this is for the full register. So just I don't know, let's just call this 0 m, I don't know. Yeah, so this is our state vector. So it's like our psi ket, it's this thing. Now what we really want to do is just calculate the kernel somehow, right? So what we want is just this thing. Now how do you get that? What we have just done is actually do this psi thing. So this state vector, it now represents our psi of xi vector, right? So the space that this psi thing lives in is just the complex numbers that raised to the power of, well, how many ever basis vectors you have for the full register, right? For all the qubits combined, you have like 2 power m different states, right? Pure states. And so like a convex combination of them, that would be our, I shouldn't say a convex combination when the real thing is like this square, or not even square, the norm square of the elements add up to 1, but you get what I'm saying, right? So under that thing. So yeah, it's just this thing to the, so yeah, it's still just this thing to the power of 2 power m, right? So that's 2 power m basis states, and so this thing is spanned by that. Sure, some of the things that would actually lie in this full set aren't there. Like you can't have something like a negative probability and stuff like that, but you get it the same. Or just the full probability thing exceeding 1, that's very weird. That should always be equal to 1, or being less than 1, that also doesn't make sense. But still, it's spanning a much higher dimension space than what it was spanning before, right? This xi thing, it was spanning what? It was spanning r to the power of n, right? But now these n features, you have encoded them in some m which is comparable to n numbers, right? Usually m is equal to n, but like whatever, we don't care. It could be more than that. It's like slightly more. What's the big deal? Like, every single qubit you add is just twice more number of basis vectors. So it's an absurdly high dimensional space that we're going to lie in. So it's like this space spanned by 2 power m basis states. It's a pretty large space, and the way this thing works, this epsilon, is that some of these gates are like 2 qubit gates. So there's like a whole lot of weird stuff going on. There's like some entanglement, there's some things which are like not very reversible. So all in all, whatever you sent in, you can't just like get that back. So now it's a completely different vector, and it's a much higher dimensional vector. Yeah. But now what we have to do is do the same thing on some xj, right? So essentially the vector that we got was this, whatever this epsilon transformation is. So epsilon just takes parameters xi tilde and it does something based on xi tilde, right? So if you don't know what I'm talking about, just go search parametric quantum gates and you'll understand. And then after that, it just applies quantum gates and we get this psi gate outside. So this quantity, our phi of xi vector, that is this thing, epsilon of xi vector. I'm just gonna call it xi vector at this point. This whole process of normalizing this thing, just kind of forget about it, right? That's also now a part of your epsilon. Just assuming that epsilon does that inherently somehow. Okay. And your phi of xj would similarly just be this thing. There's also a 0 cat over there. It's just this thing. So now what you want is just this quantity, right? And since like we are talking about quantum mechanics now, I'm just going to write it like using the bracket notation. So forget inner product spaces, just think of it as bra and get. So yeah, convert this whole thing, this xi thing, so to a bra, right? Take a Hermitian transpose. What do you get? You just get the bra 0, and then this thing having the Hermitian transpose, but then it's a unitary matrix, right? Remember, all our quantum gates are unitary matrices. So unitary matrices have the property that the Hermitian transposes are also their inverses. So essentially what you're doing is just epsilon xi, right, inversed. Yeah, or you could do it the other way around, like you could have a j over here and an I over here, doesn't really matter. So let's just use that instead. So instead of taking this guy's transpose, we'll take this guy's Hermitian transpose. So you'll just have an xj instead, right? So that's this thing, that's our so if you can, yeah, you should probably think of it as as vectors. Yeah, that's probably the best way to be thinking about it. So then we are just thinking about the bra of this, right? And then we just multiply by this ket. So it's just this quantity, but replacing these values. So this is replaced by this quantity and this is replaced by this quantity. What we get is this. Right, cool. Okay, now here comes a bit of a twist, and personally I don't like this, but to actually be able to do anything, instead of using your inner dot product, what you could be doing is just taking a norm and squaring that. Yeah, it's a complex number, just take a norm and square that. That solves a lot of stuff. right? So in your linearization, instead of having something like this, now the new term that you would have is something like this. Yes, it's very ugly, I get it, but yeah, I mean, what can you do? That is kind of what it is. Sure, but like, don't worry, this is also something that's that you can actually build with these kind of things. And yes, it lacks quite a lot of properties, but it's okay. It's okay, I think. I don't even know how to convince you that this is fine, but that is what people use because it's convenient and because you can actually build something nice with it. But yeah, so it's essentially this that we are using now. So our k of xi xj is this quantity, which if you see, it's just like the probability of your like phi xi vector, being devolved into this thing, this phi of xj vector thing, right? But yeah, so as I was saying, this is much easier to compute, and so to compute that, you just take a norm and square that. Now this actually makes sense because this is very much similar to doing a bunch of operations on your quantum machine. So what we are doing is we're taking this zero ket vector, we are encoding it, right? This epsilon xi is like a unitary matrix. It's just a bunch of gates really, and it does something to it, and we get some sort of vector. Then we decode the vector, right? So this epsilon xj inverse, it's exactly the inverse operations of whatever epsilon xj would have done, and so those are also just normal quantum gate operations in the end, right? Yeah. So we invert the whole thing, which is also just like adding more gates essentially, and then we get something, right? So you get some ket psi dash as this quantity, right? And so this whole thing is just this, it's this thing, right? Which if you see is pretty much just measuring your psi dash and seeing whether or not, like at what probability is your psi dash going to be collapsing to our zero ket, right? Because this is quite literally the probability that your psi ket would be measured to zero. So what do we do? What do we do to like calculate this number? It's pretty easy. We measure our psi ket. We can create psi ket like indefinite number of times. We can always reproduce the whole thing because our xi vector is just like some real numbers. We can always encode it, right? So we do a bunch of gate operations, doesn't matter. We just convert our zero ket to psi ket, psi dash ket is more like it, and then we measure, and there you go. That's one observation of this thing, right? This is just a probability. So if it's a zero, then you say okay, we measured it to be zero ket, otherwise we didn't measure it. And what's the probability of it being a zero? It's exactly this thing, right? So this is the probability of psi dash being equal to our zero ket, right? So this is something you can empirically get, and once you have gotten that, that's your value. That's the value that you're looking for. So we can run some like t trials, and for every trial all you have to do is just encode this into like I don't know, let's just say you have like n of these gates, right? So at the worst case scenario, you would just have like some 2n or 3n operations, right? Actually, okay, so all the m qubits have to be done. So let's just say like 2m or 3m operations, right? So this times some order m. So I just actually write this whole thing in order notation. So just order t times m, right? And this is going to be done twice, so in the encoding and the decoding, and then you just have a bunch of measurements, which is also like order m. So yeah, that's the complexity for doing the kernel, for calculating this k of xi xj, right? Much easier than if you were going to do this the traditional way. Traditional way would be just to actually either just to do a kernel trick, which isn't always possible, or actually calculate what this phi of xt is going to be. And this is where the problem is. Over here you have 2 power n basis states in the space that your scikit lies in. You have 2 power m basis states. So to get the same kind of expressibility, you would need to have 2 power m variables. And do you understand why this is such an advantage? Because 2 power m variables, it's going to grow exponentially with m. The higher your m becomes, the worse it's going to be, right? So over here you have like order t times m. There you would have something like order 2 power m. That's very bad, right? Yeah, actually, yeah, okay, that's pretty much the same. So 2 power m multiplications, and you have to add all of it up, and then you have to square it. That would be the brute force method, and that's probably what you will have to do when you don't actually have a very good kernel function. So I am trying to say is that this is much better. It's way more advantageous. Of course, it has some problems, that it's just an approximate thing, that we cannot actually like get the real value of this thing, right? Because you can only have like t trials, but still it's much better, I would say, right? Yeah. Okay. Right. And yeah, you could say that, oh, what if the probability is very less, then you have to like wait for a long time. So I would say just make it 0, right? What's the big deal? So you can kind of just approximate it, pixelate your thing very much, essentially. But this works. People use it and it actually works. And of course, this is not always going to work. There are cases where you like require a lot of precision, or where a classical feature map is much better, right? Even with less number of extra features added up, it's much better. In those kind of scenarios, this is just an overkill and actually not even going to give you good results. But there are problems. There are these SVC problems where this is probably the only way to solve it. For classical sort of SVC, you cannot solve these problems, right? And I don't know, just take a look for these things. It's all available online. So yeah, that's one thing. Now this is very much closely linked to another thing, which is so it's like quantum variational classifier. So that's very much like a neural net, I would say. I don't even know what to call it, but just as we were like encoding your input vector, so whatever features you have, we're encoding that as a gate. You can similarly, after encoding, instead of just like calculating some sort of kernel, you can actually do a bunch of other gate operations, which will be like parameterized by some parameters which you can change, right? So what we'll do is, you have some 0ket, some m-bit register, you pass it through a bunch of gates, which combined will just call like epsilon of xi vector, right? Cool. Then you pass this through something else. You pass it through some sort of a model. So I don't know what to call this thing, but like let's call it like f of theta, right? So it's some sort of function which is parameterized in theta. Theta is just some like real numbers, just as xi vector was, is also a vector. It's just a bunch of numbers pretty much in 0 to 1. Yeah, and so it does something to your state vector, and then finally you get something outside of it. And once you get outside, you can just kind of measure the thing, right? I was going to say something, I kind of forgot what I was going to say. Yeah, right. You just measure it. You just create this histogram sort of a thing for different states. So you have like the 0ket, the 1ket, etc, etc. So like the probability of 0ket, probability of 1ket, so on. So yeah, so essentially what this thing is, it's very much like the output of the last layer, your final layer in a neural network, right? It's like when you apply a softmax function and you get a probability distribution. It's very much just like that. And so with this you can actually like create some loss function, right? So you have some cross entropy loss or whatever. And yeah, so with this and with of course the target yi, you have your loss function. So it's loss of, actually this should really just be involving the side since it's an input, but whatever. So it's the loss, I'm just gonna call it the loss, not write the inputs to this function. But yeah, and as any machine learning model goes, we aim to minimize this loss. And so yeah, I was going to say something, right? These probabilities, although we kind of find them empirically, we can also get them analytically, right? So yeah, like before measurement we would be able to get these analytically, and so if you can write down equations, you can also write down gradients, and once you can write down gradients, you can do gradient descent. And so you can actually vary these theta parameters, right? You can update these theta parameters like this. There you go, the usual stuff that we always do. You can just do gradient descent and you will have the optimum theta or locally optimum theta, right? And yeah, so what we have essentially built is a neural network, pretty much, except that you don't have like actual perceptrons anywhere, but this is some sort of a function which acts like a multi-perceptron there. So it's working like a neural network, right? Yeah, that's, I think it's pretty much the same. So the only problem with all of this is like you cannot actually get the state vector right away without all of these measurements. So you will probably have to run this thing, these gates, a bunch of times. And the way these gates are run, so in quotation I'm saying run, is that they are quite literally run as instructions on some machine, right? So yeah, it's actually going to take a bit of time every time to like, so whatever t iterations you do to get this distribution, it's going to take some time, right? Yeah, the analytical functions are very, easy to calculate. Like you would certainly know what distribution this is actually going to be like at the time of training, because you can just calculate based on whatever xi you have your what was I going to say, your final state vector, and then you can do gradient descent, no problem with that. But at the time of testing, that's kind of a huge problem, isn't it? Because we want it to be like fast, and since we want it to be fast, we actually want to do it empirically. Yeah, that's the whole point. Because if you just like going to calculate it classically and then figure out the probability distributions and stuff like that, that's just unnecessary and also beats the whole purpose of doing this. This is a very much hardware level stuff, right? Like these are just gates. You don't have like anything on a higher level than that. You don't have like ALUs or some like instruction, nothing. You don't have any of that. You don't have any high level language involved. These are all just gates pretty much. Of course these are represented as like I say instructions, right? It's just instructions in some language like Quill or whatever, but in the end they are gates. They run in like order 1, and you would say okay, even multiplication is order 1, but you get it, right? This is very different. This is much different than running even something as simple as addition, because that would take some cycles. This also will take some cycles, but this is much faster because it's just like literally running gates, and it's doing a bunch of things which would actually require like a lot of computation to be done on a classical computer, right? Well, that's just what I had to say. See you guys in the next video.